I was going to steal the 3 minutes that they left for me. And so thanks very much. It's always interesting to come in. I was really excited. I walked into a room and it was packed. There's people all lined up around the sides. And I thought, man, this is exciting. People really want to hear what we've got to talk about at Schneider. And I didn't realize it was Facebook, Microsoft, Equinix, and Google talking about fiber optics before me. So for those who are just sticking around, we had a little bit of things that we've been announcing this week at Schneider. We've been looking at open compute. My role in Schneider is looking at the data center for the entire corporation in terms of making sure that our R&D portfolio is getting lined up behind the trends that we see happening inside of the data center. And we see a lot of interesting things within open compute. And we wanted to share some of our learnings over the last 6 to 9 months as we've been researching different areas of this. There's a lot of things and a lot of benefits that are out there about open compute. A lot of it is at the IT level. There's a lot about the community and sharing and so forth, and we believe in all that. However, there's some things that we've seen where, there's always claims coming out about 40% less expensive, 34% less expensive, 15% more efficient. And one of the things that we like to do is always look at those models and say, compared against what, and try and help the industry understand where some of the savings come from and what are some of the things that you might want to look at. So if we go through this from a power architecture standpoint, when we started digging into open compute, we really found that there's an awful lot about what's happening at the rack and a lot of detail around the IT level, but there's very little about practical information about the upstream power architecture and how should I really deploy this. And particularly, we think for OCP to get broad adoption, we need to talk about how do I do it if I go into a mixed environment, and that we need to answer some of these questions. So if I'm a co-location provider like Equinix before us, they've got to be able to build a data center that can accommodate open compute architectures as well as traditional. And do they do that in the same data center, or do they have to build 2 different ones? And so these were some of the questions we started challenging ourselves with. And what we did is we really started getting into the details about what are the cost trade-offs when you do an upstream power architecture. We challenged ourselves to look at it from a different way than maybe we would have done traditionally. So what we did is we built this model. This is a little bit of the details of the model that we built. And we started by comparing against traditional data centers and what does it look like. And we did everything from the medium voltage all the way down. So that's what our cost model looked at, medium voltage all the way down to the power supply, and started comparing what things look like. And this is all published in a white paper. Everything I'm talking about today is available in our white paper. It's number 228 that you can get from our website. Okay, so all the details are in there. So jumping ahead a little bit, we wanted to give you a little bit of flavor of what do the savings look like. And we took a traditional 2N data center. I would call this kind of a typical tier 3 that we see people build. And we said, what if I take it and I'm going to do kind of in the spirit of open compute, I'm going to go vanity free. I'm going to strip absolutely everything out that's unnecessary. And that's what we call our open compute specific, 1N. So it's a 1N design, 1N power coming into the data center. And then we started looking at that and saying, well, that might not be right for everybody. In fact, it's probably not right for almost everybody, in our opinion. And we started adding things back in that we thought made sense. So we didn't go from a traditional and take things out. We started with, let's take everything out that we possibly can. Where do we end up? That's where the cost is. And then we added things back in that we thought made sense. Okay? And I'm going to walk through each one of these a little bit to give you a sense of what's happening. So this is a typical one line of a traditional 2N design, and there's a lot of things in here that we put in quotes, belts and suspenders. There's some things in these traditional designs that we actually think are quite crazy in many cases. One of the key things that happens in the philosophy with traditional designs is they have dual power supplies in the server, okay? But they do not rely on those dual power supplies. What happens traditionally is people build complexity in the upstream power architecture so that if they have to go and do maintenance on one side or the other, they're still providing power to both power supplies, okay? This is kind of interesting because you have dual power supplies and it's really a lack of trust between the IT people and the facilities people that's driving some of these decisions, okay? There's also things like SLA and contracts that get into it if you're a colo, but fundamentally, really, it's a cultural problem that we have as an industry between IT and facilities. And to me, this is one of the exciting things about open compute, is it's really obliterating that. There's things that are traditionally in the IT world that now are coming into the facility infrastructure, and like the power supplies, and things are getting much more optimized. So that creates a lot of exciting opportunities. And you see there's generally a lot of work that's done. Say in this case, we paralleled some UPSs together. You can see in the green circle on the right, there's extra breakers that people put in. So they don't want to take one side down and do the maintenance. What they want to be able to do is take individual little pieces down. Well, all of that adds cost because I got to build in extra breakers. Right? And by the way, I work for Schneider. I mean, we sell a lot of breakers for a living. So, whenever I do these presentations, somebody gets angry in the audience. But this is some of the things that we started looking at, saying, why do I have all this extra things in there, and is it really necessary? Maybe it is, but we really questioned it. So we really took this and started saying, what are the things I can get rid of? And there's extra load banks, ties, UPS output breakers, all sorts of interesting things that we took a look at. And then if you compare it, this is what our one line looked like when we stripped out everything we possibly could. So we kept generators. You have a utility power coming in. You've got one piece of switchgear effectively coming in at the LV level, and it comes on down to the pod, and then you can see you have the power supply units and the battery backup. So you eliminated the upstream UPS. You've got everything as a power supply unit and a battery backup. There's a problem here, though, is that if you want to go and do maintenance on any pieces in this, say there's something with the switchgear, something needs to be done, the problem, your only alternative really is to take the load down. All right? And we don't think that's really practical for most people, but this is where we started. We said, let's strip out everything, and then we'll only add back what we need. We'll be vanity-free, as we like to say. So this is really minimizes the breaker count, very simple design, and really a stripped-down cost reduction. And we ended up with these types of numbers, that a power architecture costs $2.77. That's just based off the one line I showed you. This is our best estimate of what people will really pay for that architecture to get in. So, it comes in around $2.77. And the open compute comes in at at $1.53. Now, what was interesting to me, though, is we started digging into what is the drivers of those differences and what's causing it and where's it come from. So we did this little diagram. What we found out was that 31% of those savings, so 87 cents per watt, is simply because I made a change to the architecture. I went from 2N to a very simple 1N. That's where my savings come from. Okay? Then you take a look. You actually the rack system, an OCP rack, actually costs more than a traditional rack. Okay? You got the power supply, you've got the shelves. There's just more things that are in that rack. In general, we estimate that's about 3 cents per rack. If I eliminate the upstream UPS, this does not include the batteries. Okay? This is just the UPS equipment itself, not including the batteries. I save about 22 cents per watt. The batteries in an open compute architecture compared to a traditional UPS with sealed lead acid batteries, you're going to pay more in an open compute architecture for those lithium ion batteries. It's about 15 cents when you net it out. Okay? So the batteries actually cost more. Lithium ion batteries are still 2 to 3 times more expensive than sealed lead acid. And we'll talk some more about that. Whoop, well, wrong way. There we go. And then this was the one that was quite surprising to us, and we're going to get into a deeper conversation on this, is the cost of the power supplies. So for us, from the part of the world that we live in, when the power supplies got pulled out of the IT equipment and consolidated into the rack, right, we started viewing that now as part of the physical infrastructure and part of our perimeter that we needed to address. So we started modeling out what's the cost of that power supply relative to traditional 42 1U pizza servers, dual power supplies in every one. And I'll tell you, we spent a lot of time debating this internally, and I can tell you the model's very sensitive to this, is generally what we found is those power supplies in a traditional model are severely oversized. And you're spending a lot of extra money in the power supplies, and there's quite a bit of savings to be had by consolidating that into one power supply in the rack. Okay, so you have one power supply in the rack, it's working as both the UPS and the power supply, but the reduction, taking those out of the IT equipment, came out to be 34 cents. And really quite significant in our minds anyway. So we took a look at that, and we said, 2N probably is still important. All right? Now, unless you're running a data center where you really can afford to have your applications fail over, if there's any maintenance or so forth, we don't think everybody can be that extreme. Most people that we talk to aren't really building that way. They still want to be able to have 2N, 2 different feeds from 2 different substations in order to get some level of concurrent maintainability. If the one side goes down, I don't want to have to be running my generators, right? So that's generally what we think. So this is kind of a middle ground. We added some things back in to get 2N. Here's what that architecture looks like. And the key thing we did here is we did reduce complexity. We eliminated unnecessary cross ties. We eliminated breakers that we didn't think you needed. And the fundamental philosophy here is that we trusted the IT power supply. Okay, so it's no longer a philosophy where, hey, I'm on the facility side, I don't trust that IT guy, so I'm going to build in a lot of complexity in order to make sure he's not going to call me when one of his power supplies fails. I'm going to always supply power to both power supplies. That drives a lot of complexity. All right, so I know I've emphasized this again, but it really is a different way of looking at things that I think is important for the industry to embrace. And we save costs because we only have the battery on one side. So if you look at the bottom, there's an OCP architecture. So in effect, what we said is we modeled this out saying I'll have two power supplies, okay, in the rack so that I get two ends. So I have two power supplies powering the bus. If one of those power supplies blows up, I still run because I got something happening come feeding from the other side. But we assumed you only needed one battery backup unit, so we didn't double up on the batteries. Okay? So that's kind of what we call the open compute specific 2N architecture. This architecture will only support open compute style loads. It does not accommodate traditional. So we looked at that and we said, okay, what's the cost look like on that? In this case, it's $2.77 versus $2.08. 40 cents is coming, all right, between the traditional, right, belts and suspenders, traditional tier 3 design that people typically do. Okay, 40 cents is coming just from the architectural changes. And then the rest of the numbers stay the same, as I showed you in the previous model. So again, UPS 20 cents, I'm paying more for batteries because we modeled it against sealed lead acid. And here's where you find yourself. So what's interesting on this then is we said, after going through each of those models and designing it, is what if I have a mix of open compute and traditional IT? What do I do? And we really think, this is going to be something important that the industry deals with because people are going to build data centers and they're going to need to be able to, colos in particular were what were in our mind. If I was a colo provider, I would want to know the answer to this question because I'm going to have customers coming in that want to be able to put in open compute, but they're also going to have people that are going to have cages that are still traditional. What if I have a mix of those two? How would you design the data center to accommodate that? And then what's the cost penalties associated with having that flexibility? So we started working on that and modeling that out. And then this is where you came out. So we called this one the simplified 2N. And what we found out is, so now instead of the $2.08 for the specific to open compute specific 2N, I've gone up to $2.15. But then we modeled out separately what's the premium that you might end up paying if you've got regular IT power supplies coming in. And we thought this was important to separate out because depending on what you're doing, where do you measure the cost of the IT power supplies and how do you do that? So we wanted to make sure that we were capturing that. We didn't want to cheat, in other words. We wanted to show where those cost differences are. And those range anywhere from, if I went and built a colo data center and everybody who deployed in that was open compute, your cost difference is, it's zero. It's the 215 versus the 208. All right, so you're paying a 7 cents incremental penalty in order to have the accommodation. If everybody goes open compute, that's what you wasted in cost. And if everybody go in with traditional IT, then it's going to be an additional 23 cents per watt is what's being paid for those power supplies. So if I'm a colo, maybe I don't care because that's being paid for by the tenant coming in, right? If I'm an enterprise guy and it's my stuff that's coming in, then maybe I do care. Okay, so we just wanted to highlight that this is really a significant driver. So again, now here's the example. In this case, in order to accommodate traditional IT, we chose to centralize the UPS, but we only did it on one side. So you don't necessarily have to put a UPS on both sides to get concurrent maintainability. I can just put the UPS on one side. It's really more habit in the industry that people do both sides. You don't have to. So we chose to just do it on one side. We minimized the output breakers on the UPS because we figured if you're going to do work on that, don't put in all the extra output breakers. Just take the UPS offline, work on it. Don't worry about being able to isolate each individual piece of the UPS like a lot of people like to do. And then you can see at the bottom what would happen on the OCP things that you deploy is you no longer need to deploy the battery backup unit. If you trust the central UPS upstream, your battery, your energy storage is already there. I can just do a regular power supply. And there was a side benefit we started calculating. If you deployed this way, where you centralized the UPS and chose not to put the batteries in the rack, you're going to save about 2 U a rack, 2 to 3 U per rack. That adds up to a significant amount. If you start going towards megawatts of power, that ends up to a significant amount of U space. So that was also an interesting finding that we said is what's more important, getting the batteries in every rack, or do I centralize them to free up U space? I don't know what the right answer is on that, but it's an interesting discussion point to have. So that's something to think about, is what's the better way. So in this case, I can very easily deploy some regular traditional IT right next to it. I could put in traditional OCP. I don't have to put the batteries in the rack. You could, it doesn't break anything, but to us it would be a waste of money, so we took it out. Okay, so that's the example that supports both types of those loads. And again, we wanted to hit a little bit on this load mix and what happens, because this was really quite interesting for us anyway. Maybe we're just power geeks, but this is what we started getting into is, what is the premium on a percentage basis depending on the mix? So again, I start with the $2.08. I got to pay 7 cents just to get the architectural premium, right? So if I go to a centralized UPS with a lead acid battery, that's basically the 7 cents that you'd net out. So you got to pay a 3% premium, but if I start getting in these mix of loads, again, looking at now the power supplies, even in a traditional model, are part of the physical infrastructure. What you start seeing is if I have 50% OCP loads, 50% traditional, you're probably paying about 12 cents a watt more for those IT power supplies than you needed to. And then if I end up with 0%, you start seeing where the numbers come in. So it's like 23 cents. So, to us, this was just really an interesting topic that we started getting into. Is all of a sudden, we thought we started this exercise just looking at it from one point of view, and then we stumbled into this, geez, the power supplies are really important. And I don't know if other people have looked at this. We're not aware of anybody else who's really talked about this. And where do I put the energy storage? How do I deal with the mixed loads? So for us, this was quite a finding that we dug into. And I'll tell you, this was an incredibly contentious debate internally as we were working through this. And we reached out to people in the industry. We could not get good numbers on this. This was incredibly frustrating. We're trying to put these numbers together. We could not get reliable data on what people are doing with the traditional IT power supplies. And so we got estimates that ranged everywhere from, this was what we ended up using as our model, but we varied it from 2x oversizing to 4.5 times oversizing. No matter what, there was oversizing. So it came out to about 3 times is what we used, but it's got a significant impact on your cost. All right, so if I'm going out and deploying traditional IT versus open compute, understand that the power supplies, at least from our point of view, had a big impact on it. And why aren't people sizing power supplies correctly is quite interesting. Second thing, the warning is, if I go and deploy open compute and I'm deploying it, we assume the following, is that you're going to deploy a rack that's at 10 kilowatts per rack. So the power supply we put in was 12 kilowatts, because you have to have a little bit of oversizing. So we assumed we were perfect on open compute, and we assumed we were not perfect on the traditional side. But if you deploy open compute and you don't utilize if you don't deploy at 10 kilowatts per rack, if you do not utilize that power supply, you are wasting money. So you have to design, what is the IT, what is the power load, what is your load per rack, and you want to match power supplies and the upstream architecture to meet that. And the only way you know that is by determining what is your IT, what's it really going to draw, and then sizing things appropriately. If you do an open compute style at 5 kilowatts per rack, and you deploy 10 kilowatt power supplies, you're just wasting money, and a significant amount of it. And potentially efficiency too, depending on where the efficiency curve is of the power supply. So this became a really important issue, at least we thought so. So we wanted to share it with the community. Our model ends up being highly sensitive to that, so I won't go through the details. I think I hit this. So, but this is it could be anywhere from an 8 to 26% premium that you end up paying. So it's really a thing. Look at the power supplies. Let's make sure we understand that. And one of the things that we did is we took all of these designs and we are making them freely available. So we already have a library of reference designs. These reference designs that I showed you, the one lines and the details on that, are freely available. Anybody can come and get them. We also developed some trade-off tools on open compute versus traditional, and what's that cost comparison that I ran through. So we have some tools showing that. And then as I said, we've got a couple of different white papers. Some talk about VRLA versus lithium ion. Okay, and I have a couple slides to talk specifically. I'm going to break the presentation 2 parts. This was talking about the reference designs. I got a couple other slides I'll share in a second talking about VRLA versus lithium ion, and I'll share a little bit of position on that. So those are the tools we have available. Key takeaways: to increase adoption. We think these power infrastructure questions have to be addressed. We intend to put this out into the market, into the community in order to start the conversation. We think we've got a pretty good starting point, but I'm sure there's a lot of bright people who are going to look at it and maybe have some other ideas. But we got to talk about the upstream power architecture in conjunction with what we're doing at the IT level in order to really achieve the goals that we all have. And we do have some other sessions going on if you're interested in getting more detail. We have a session in the Expo Hall at 3:40 where we're talking about work that we've done to help people deploy open compute type architectures. And then tomorrow at 1 o'clock, the reference designs I showed you, we're going to walk through those in detail with one of my colleagues. Okay? So that's that part. I got a couple minutes, so I have time. I was going to jump a little bit on lithium-ion batteries. We announced last week that we are, and really I credit Open Compute an awful lot with really highlighting the benefits of lithium-ion batteries in the industry. There was the first one that really came out and said, hey, we should go to lithium-ion. We took that very seriously. We've been looking at it. Here's basically a summary of lithium-ion versus VRLA. Last week we announced that we are supporting lithium-ion in all of our three-phase UPSs, and we disclosed what our roadmap is for that. They basically have double the lifespan, so they go 10 to 15 years versus 4 to 6 years. This is the key metric that's happened over the last couple of years, is the lithium-ion batteries have basically come in line where I can deploy them, they'll last for 10 to 15 years, they're 2 to 3 times more expensive, and about a third the size. When they're 2 to 3 times more expensive, as soon as I do one battery replacement, they've paid for themselves. It's really pretty easy math. Okay, so if they're twice as expensive up front, by the time 4, 5, 6 years go by when I would have had to replace my lead acid, I would have offset that cost. And that's on an even runtime basis. Way less, faster recharge time, greater than 1,000 cycles versus 400 cycles. To us, this opens up all sorts of interesting opportunities of things that we can do to make the data center more efficient because you've got the ability to cycle the batteries much more. In the old days, we had to, we put the sealed lead acid batteries and you had to, put a shrine around them and protect them and make sure nobody looked at them the wrong way because something bad might happen. Lithium-ion batteries, you can kind of put them in a back room. If it's a little warmer, it's okay, right? They'll last a lot longer. They'll, power can go up and down. They'll cycle, and the last 10 to 15 years is, a couple of people said, well, what if they catch on fire? We'll just ignore that issue for a second, right? But that's something to think about. So specified, this is where, again, they just in general can handle a broader environment. And really, in my mind, I joke about this. I've been in this industry too long. In the early 90s, I actually sold against a centralized UPS by selling a bunch of decentralized UPSs in the bottom of every rack. And there's some good reasons to do that architecture, similar to how Open Compute's done it. And it's not wrong. There's some benefits to it. One of the drawbacks, though, is you end up with a lot more batteries, a lot more dispersed inside of the data center. Are you comfortable with that or not? That's a choice. It's not necessarily right or wrong. It's a choice on how you might want to do it. But the thing is, there's also benefits to centralizing. You free up space, use space in the IT rack, like we mentioned, less batteries to manage, and so forth. So, if you decentralize, better fault isolation, and you do get better incremental deployment. So I can go, I only deploy the battery energy storage capacity when I need it. So there's benefits to both ways, and one of the things we wanted to make sure is that we were separating that conversation out about, do you want to go to lithium-ion or do you want sealed lead acid? And then you can decide on where do I want it to be in my architecture. Do I want it at the rack? I could do it at the pod level. I could do it at the traditional low voltage level. All of those are a separate discussion, but lithium-ion is a key enabler to allow us to have really a more intelligent conversation about that. So we're driving very hard, bringing lithium-ion in all of our UPS ranges. Okay, we've announced publicly what we're doing on the three-phase side. We're announcing publicly that we've got Open Compute power supplies, battery backup units, Open Compute racks, because we really do believe these are, both architectures have a place in the industry. And that's what I had. And I am down to 1 minute and 15 seconds. By the way, I want to bet, because some people bet me I wouldn't be able to do it in 25 minutes. So for those of you who are cynics, I did it. So thanks very much. I'll hang around and be outside if anybody has any questions. Thank you.